Okay, so remember what we were doing here. This is kind of a weird concept. We're adding up areas under curves. That's an important thing to be able to do in math. And the way we're doing this is we're going to pick convenient shapes to add up. So the areas are easy to calculate. It'd be very difficult. I mean, at this point, we have no way of calculating exactly the area under that curve. But that's what we're coming up with is a trick for doing that. Our trick revolves around, again, we're going to cut this thing in. We're going to make vertical slices of uniform width, cut this into pieces, and estimate those small vertical pieces of area by vertical rectangles. The width is always just going to be the same. It's just going to be the width of the area that we're slicing up divided by the number of slices, right? A is the left edge, the x value of the left edge of our area. B is the x value of the right edge. So B minus A is the total width divided by the number of slices, n, right? And when we do that, we said we build up these rectangles. The width is always just delta x, which we just calculated, b minus a over n. And the height is just determined by which part of the interval we're using to determine the height of the rectangle. Are we using, there really are three options. We could use the value of the function at the right edge of the rectangle. For an increasing function, that's going to give us a big overestimate, right? Going to give us a big rectangle. We could use the value of the function at the left edge of the rectangle. So for an increasing function, we're going to be undershooting. And then if we want to be maybe even more accurate, we could even use the value at the midpoint, okay, where we could just input the x value that's halfway between the two edges of the rectangle, okay? As I mentioned yesterday, our trick is going to be, and you guys kind of came up with this, our trick is going to be if we just let the number of rectangles go to infinity and took the limit of the sum of all those areas, it's going to give us an exact answer. So therefore, we're just going to use the one that's most convenient, which is the right edge, right? And the other thing we talked about was, let's see, I think it was back here, maybe, yeah, right here. Right, we said if we want to be able to identify the x value of the right edge of any one of those rectangles, to be totally general, we'll call it the ith rectangle. We do that a lot in calculus. We're going to have some index variable, and it could be j, could be k, could be I. It's usually one of those three. That's the index variable that's going to, it's going to vary from the first to the last, and it could be any one in between depending on what the value is. I is going to increase from 1 up to n, whatever n is, right? So to get to the right edge of the ith rectangle, what did we say? We're going to start at A, which is the same thing as x sub 0, and we're going to take I steps of width delta x, which just means we're stepping across I rectangles until we finally get to the right edge of the ith rectangle. So x sub I would then be A plus I times the width of each step, which is delta x. Okay? And we use this finally to do something pretty interesting. We did something like this. We were able to actually pick something like n equals 50, and we were able to estimate the total area we get when we add up 50 right rectangles whose heights are determined by the right edge of each interval, right? And we came up with something that was a number, right? Which is pretty cool. Yep.
So if you increase the amount of rectangles, the resulting area is just going to get a little bit smaller.
Right. It's just exactly, the overestimate is going to get smaller, and if we used left rectangles, the underestimate is going to get bigger, and they would just combine, they would merge on the exact area which we would get if we let the number go to infinity, took that limit, okay? So today, this is big day. So today we're gonna do something important here. We're gonna do, let me see what we're doing here. Okay, so we're gonna do the same thing, same function. We're looking at this guy, right? The curve is the function f of x equals x squared, and we're gonna go from 1 to 4. Okay, those are A is 1, B is 4. I feel like I'm missing a page here. Yeah, I feel like I'm missing a page here. Where did all this come from? Oh, right here. Right here. Yeah, let me grab all this stuff. Yeah. Okay. I'm going to put this all on one page for your notes so we can, oops. There. Okay, finally. Got it. Okay, so let's review this. If we've got the function f of x equals x squared, and we want to come up with the limit of all the, we want to come up with the sum of all the right rectangles, well, what is that? That's just going to be the width of each subinterval, right? There's delta x times the height of, it's this is what it is, right? We're going to add up the value of the function at the right edge of each subinterval. So we could call this stuff right here, sometimes we call that r sub I, where r sub I equals right edge of ith subinterval. Yet what we mean by subinterval? The total interval is just the total area from 1 to 4, right? The subinterval, each subinterval is going to be that little section, that little piece of the total interval that constitutes one rectangle, right? So the ith subinterval, the right edge, is just a plus I delta x, like we just said, right? We start at a, and we're going to walk to the right by I steps of width delta x, okay? The value of the function at the right edge, this whole thing right here is just giving us the height of the ith rectangle. Everybody see that? Okay. And then what is this? This part right here is just the width of every rectangle, including the ith rectangle. So height times width gives us area, right? So this whole expression right here, we're just summing up all this stuff right here. That whole thing is the area of the ith rectangle. Everybody see that? And what are we doing? We're adding up all of the areas of the ith rectangle as I goes from the first to the last rectangle. That's pretty cool. That's going to add everything up for us. Okay, so delta x we know is just b minus a over n, so we just pulled that out front to get rid of it for a second. And a plus I delta x is just b minus a over n. So we just did a bunch of algebra from this point forward, right? We plugged in values. Okay, we know that a is 1 and b is 4. So if we plug in 4 for b, 1 for a, b minus a is 3, so that gives us 3 over n, right? We know that our function, f of hand in this case, is just hand squared, right? So what if we square that out? If we square out that binomial, it just gives us that expression, that trinomial, right? And then we just broke it into 3 separate sums. So we summed up the first. I'll kind of try to draw some little. So we summed up the first term, we summed up the second term, and we summed up the third term separately, right? Make sense? Okay. Well, what can we do then? We got this 3 over n out front that we'll just leave there for now. The sum of 1, we get the sum, okay, with sum of 1, and what did I do here? Okay, I guess I actually, yeah. So I redistributed that 3 over n now. Okay, I redistributed that to each one of these. So I get 3 over n times the first sum. 3 over n times 6 over n is 18 over n squared times that second sum. And then over here, I'm going to get 27 over n cubed times the third sum. And you might wonder, where are we getting those sums? Well, summation formulas, right? That's all those are summation formulas. We're using i's instead of k's, but who cares? Same thing, right? I's and k's interchangeable. Okay, we would just switch all these to i's for our purposes. So what is the sum of 1? Well, the sum of c as I goes from 1 to n would just be c times n, right? Well, c is 1 here. So 1 times n is n, right? So that first sum, this whole thing, I'm running out of colors here. Let's see, we'll go dark green. Oops. Undo, go there, go there. So that sum becomes n, right? Next one, 18 over n squared times the sum of I as I goes from 1 to n. Well, that's this formula. Change the k's to i's. The sum of I from 1 to n is n times n plus 1 over 2. So there it is. There's another. This sum turns into that. Okay, and then finally, the sum of I squared is right here. So we're going to get n times n plus 1 times 2n plus 1 over 6. Okay, now look what that did. That's pretty cool. So now the sigmas are gone, and the only thing left in our formula here is what? What's the only variable left in that expression? N. How about that? So our answer is only going to depend on the number of rectangles that we choose. We already know qualitatively that the more rectangles, the more accurate it is. Do you guys remember? Did everybody see that picture I showed you? Would have been 2 days ago when I think it was 2 days ago when I pulled up. Remember, I built this little thing in Desmos where you could see as you increase the number of rectangles, you could see how much better the rectangles match the curve. Okay, so the area that we calculate depends only on n. And from this point forward, it's just a bunch of algebra, right? If I multiply these first two together, 3 over n times n is just 3. Exactly, that's just 3. The n's cancel. How about here? Well, I could cross one of those ends out, right? Cross one of those out with that guy. And then over here, I could cross out one of those ends. I'll just cancel one of those. I mean, you could do this any number of ways. Just cancel one of those ends and that end. And then now what if we just multiply these together? So the first term is 3. Here I got 18 over 2. I combine those into a 9. And then if I expand this out, I'm going to get n plus 1 over n. N plus 1 over n, doesn't that just become 1 plus 1 over n? Right? Everybody agree? I mean, I'm just algebra, just hand waving in algebra. How about on the next one? We get 9 over 2 out front. If I multiply all this stuff out, if I multiply, what are we left with here? We're left with those two things. If I multiply those out, isn't that just going to be 2n squared plus 3n plus 1? If I expand that? Okay, divided by n squared is going to give us, oops, that, isn't it? Everybody agree? If I distribute that 1 over n squared to each of those those three terms? Good? Everybody good? Okay. Okay, give me 1 to 5. Are we good so far? Am I going too fast? Okay. Okay. And this is just like, I know, I'm just curious, like from your perspective, are you just thinking, wow, that's a lot, like I'd never think to do all that stuff? But you would. You would. It's just algebra. Once you see this a couple times, what's really cool about this math stuff is that once you get good at it, like you are, you just do it and it works. I mean, every once in a while you're going to make a mistake, but if you're very careful and you go slowly and you really focus, not that often. I mean, it's just amazing how it all works. Okay, now what? If I distribute the 9 and I distribute the 9 halves, I can add up a bunch of like terms. Just trust me on this one. If I were to, we don't have to go through all the low-level algebra here, but if I add up all of the constants, I would just get 3 plus 9 plus 9. 9 halves times 2 is 9. 3 plus 9 plus 9 is 21. If I add up all the terms that have an n on the bottom, I would get 9 over n plus 27 over 2n, right? So that'd be like 18 over 2n plus 27 over 2n, 45 over 2n. What do you know? And then I only have one term with an n squared on the bottom. It's just 9 over 2n squared. Okay? So then there is my r as a function of n, the area of all the right triangles as a function of n. So what is the actual, if I want to get the exact area, what's the only thing I would have to do? I'd have to take the limit of that expression as, it's supposed to be n, not x. Let's fix that. The limit as n approaches infinity. Okay, let's do that. If I take the limit as n approaches infinity, well, the limit of 21 is 21. Never changes, right? Regardless of what n is. What happens to 45 over 2n as n goes to infinity? What happens to the size of that fraction? Goes to 0. Yeah, right? Because the bottom gets infinitely big and the top stays the same. Infinitely big denominator means 0 value for my fraction, right? So this guy, so that guy goes to 0. Same there, right? Even faster goes to 0. 9 over 2n squared as n goes to infinity goes to 0 infinitely faster than the first one, right? So what's left? 21. The actual area under the function is exactly 21. That is amazing. That's absolutely amazing. People struggled for, hundreds of years. They didn't know how to do that. They couldn't, had no idea how you could actually figure out what that area is. And then that's when Newton and Leibniz developed the calculus, that all of a sudden we could solve those problems. But that's pretty amazing. Is it kind of? Are you to a point? What's that? What you guys remember what it was as a decimal? It was like, we might have. I don't think I wrote it as a decimal. 50 is going to be pretty close. It's going to be probably, within 1, I would guess, 1-ish. Yeah, okay, so we're less than a half away from the actual answer. That's pretty good. How could we get closer faster? We could use better shapes. We could use like trapezoids, for example, instead of rectangles. We could get there faster. Why would you do that? Well, you'll see. There's a reason. There's something called the trapezoidal rule. Oh, here. Gosh darn it. Give me 1 sec. I got to tell this guy I'll call him back. Okay. Yeah, so you'll see why. There's an amazing connection with this stuff that you would never have anticipated that allows us. That's a bit of a process, isn't it? Right? I mean, you do it a few times and you understand it. I'm honestly not going to have you guys practice this a ton just because I don't want to spend the time. You'll do this again in college. You'll do it in probably more detail, but you don't have to be a tremendous expert at finding areas under curves via limits because there's a shortcut that we're going to do that's a lot better. It's analogous to, remember when we did derivatives back in the day using limits? We did a little bit of that. And then I had to duck because you were throwing stuff at me because shortly after that, I showed you the derivative rules and it became way, way easier, right? Well, I don't want you to throw stuff at me. So we're not going to do too much practice with this because I will show you a much, much better way of doing this. Okay, so this is what we call a Riemann sum when we do this. A Riemann sum is where we're going to estimate the area under a curve using a convenient shape like a rectangle. Okay, now, what did I write here? It's been a while ago. So Riemann sums generally are denoted like this. A of n, a function of the number of rectangles, is just going to be the sum from 1 to n of, now we use r sub I to mean right edge. We use L sub I to mean left edge, or M sub I to be midpoint of the ith rectangle. U is what we use for any point that we want. U could be anything, because in the limit that we let the width of these subintervals go to 0, it makes no difference. All parts of that rectangle converge on the same value. And so we'll always use the most convenient one, which is the right edge, x sub I, because it makes the math easier, right? Makes that sigma notation much less cumbersome if we use x sub I. Okay, like the midpoint is really cumbersome. Finding the midpoint, you've got to average x sub I and x sub I minus 1, and it just looks like a mess, right? So we want to use the right edge. That's the most convenient one. And here's how we get here's a summary of what we just talked about. If the limits converge on a single value, then this is how we find the area. We take the limit of the sum of f of a, oh, where's delta x? Man, I really messed that up. Holy smokes, Mr. Oya, what are you doing? What's missing from this? The delta x at the end, yeah. Right, I should have at the end of that, oops, b minus a over n, right, delta x, okay? So really an easier way of saying this is just the limit as n approaches infinity of the sum of f of x sub I, which we'll call a plus I delta x times delta x as I goes from 1 to n, and remembering that delta x is just b minus a over n, right? Taking that limit gives us an exact answer, okay? All right, so, oh, and what's this link? Let's just take a look.
Why was there an integral?
Yeah, it's a good question. Why is there an integral there? Why is there an integral there? Because that's the notation, but because integral means sum. That's the integral symbol means it's a lowercase sigma. But why would that be there? Kind of strange why that would be there. That's our trick that's coming up. Yeah, and we'll prove it. We'll actually go through a little proof where we can show that there should be an integral there. Let's maybe look at a couple sample problems. Okay, so what if we wanted to do one like, something like this. Okay, so if we've got some function f of x equals x plus 4, that's an increasing function, right? And we want to use right sums or left sums to estimate the area under that curve from 0 to 5 using 5 rectangles. These would be the pictures that we would come up with, right? They'd be those pictures. Okay, that would be the left sum. That would be the right sum. Okay, let's do the left sum first. Okay, if I wanted to do the left sum, I'm just going to take a picture of this. Okay, what would I do? I would just manually calculate those values. So if I'm going from 0 to 5 and n is equal to 5, well then delta x is 1, right? 5 divided by 5 is 1. So the important points would be at 0, 1, 2, 3, 4, and 5. The area of the first rectangle, we'll call it a sub 1. Actually, I'm going to call it L sub 1 because we're using a left sum. L sub 1 would be what? What's the height? Yeah, it's 4 because I know it's going to be f of 0, right? Because x equals 0 is the left edge of the first rectangle. So f of 0 times my width of 1. F of 0 is 0 plus 4 is 4 times 1 equals 4. So there's the area of the first rectangle. I would just add these all up manually if I'm doing a small number of them, right? Second one, L sub 2, would be f of 1 times my width of 1, which is just 5 times 1 equals 5, etc. Just add them all up. Okay? If I were doing the right sum, then the only thing here, I'm going to add all these up. Why am I doing this? You'll see. Okay? We can be efficient if we're calculating the right sum. Okay, what do I mean by that? If I'm calculating the right sum, what's the right edge of the first rectangle? 1. Exactly. So the height is going to be f of 1 and the width is 1. Aha, what do you know? Look at this. Oops. R sub 1 is L sub 2. What's R sub 2 going to be? L sub 3, right? Because the right edge of the second rectangle is the same thing as the left edge of the third. You get that? They're always going to overlap like that. The only one that's going to be different is R sub 5, the fifth right rectangle, is going to be the height of the fifth rectangle occurs at x equals 5. So I would do f of 5 times 1, which gives me 9 times 1, which is 9. So my right sum would just include those four numbers. My left sum would just include the purple numbers. Okay, make sense? So for small numbers, you're just adding them up manually, not a big deal. What if I wanted to calculate midpoint sums? What values would I be plugging into my function for the first one? 0.5, halfway, right, the middle of that first subinterval. Here I'd be plugging in 1.5, 2.5, 3.5, 4.5. Okay? All right. 13. So I'm kind of contemplating, I'd sort of like to give you guys at least one problem like this. I want to make sure you're sufficiently challenged here. Okay, what's this asking us to do? For the function below, find the formula for the Riemann sum obtained by dividing the interval 0 to 2 into n equal subintervals and we're doing a right-hand sum and using the right-hand endpoint for each. They call it C sub k. That's not what we call it. We call it x sub I, exactly. So we'll then take a limit as n approaches infinity to find the actual area, right? So you'd just be coming up with, essentially, you're coming up with that. And then you take the limit to get the answer. Yeah. Okay. I'll just put like just a couple of those on there on the assignment. Just tack those on, just so you have to just try that once or twice. Okay. And so maybe work day tomorrow to just kind of get through all that stuff. Okay. And then after our long weekend, we'll get back and I'll show you the trick, the wonderful trick. Okay. Are you challenged enough for today, or should we do a little more? Okay, you're good. All right.